Hi everyone, let's get started. This is our lecture 21st. We're going to continue our discussion on the joint distribution. And as we discussed all this for distribution on one random variable, we're going to discuss these topics for the joint distributions as well, including conditional distributions, expected values, correlation, and covariance. And during the discussion, we're certainly going to show a few examples to help you understand this a little bit better. So let's dive into it. The first one we're going to talk about is conditional probability functions, right? So here's the definition for joint distribution. Now for discrete random variable, x and y, their joint probability mass function pxy and the marginal x pxx and certainly pyy, we can, for any x value x which have a probability bigger than 0, the conditional probability mass function for y given x equals to lowercase x is given by this function, right? So py conditioned on x, those are capitals. This probability are for y value y conditioned on x equals to the joint probability divided by marginal probability, right? This is how we calculate the conditional probability. Then for continuous probability, it's basically the same, right? We just change the mass, conditional probability mass function into the conditional probability density function, right? Like this. And then the function basically becomes something like this. And you can see this is also the joint probability density function divided by the marginal probability density function for x, right? So, think about conditional probability, what we learned before, right? So this basically give us exactly the same concept what we discussed before, right? When we are talking about a condition, your universe basically shrink, right, to its marginal function or marginal mass function. The probability shrink. Anything outside of this condition x, either here or here, we're just not going to worry about them anymore, right? The only thing we're worried is about, giving this marginal condition. We forgot about y. Given this marginal function, what will be our probability, right? It's the same concept, really. So, based on the definition, here's one example. We can calculate what is the conditional probability, right? So this is the same example we used from last lecture, right? Same thing for auto insurance and home insurance, right? We already have the marginal mass function listed here. The table also gives us a joint distribution, right? And we know all this information. Now, basically what we need to do is just calculate the probability. Calculate the probability for conditional probability, right? Given one x, the marginal mass function of x, and we also know the joint function, what will be the probability. Now, here's one, we can look at a few examples, right? We can look at a few examples. Here, let's say that, I'm asking you a few probability here, right? You see the dog, it's time to think about it and some questions. But basically what I'm trying to, I give you a few equations here. Let's say this one is giving x equals to 100, right? What is the probability of y? What is the probability of y equals to 0? And then same here, given x equals to 100, what is the probability of y equal to 100? This is given x equals to 250, y, what is the probability of y equals to 100, so on and so forth, right? So I'll give you a few minutes. You can pause the video, take 2 minutes, and think about how to calculate that, and we'll pick up from here. All right. So basically what we do is that we use a function we learned to calculate this, right? Let's say for pyx 0 over 100, right? Given the condition is 100, we want to find 0. Again, give the x equal to 100. This is a condition, right? This is a condition. And outside of condition, we don't even need to worry about it, right? So this is, we only need to worry everything that, all the probability that x equals to 100, which basically are shown here, right? So this row shows all the cases or all the probabilities that x equals to 100. So this is 0.2%, 20% of a chance x equal to 100, y equal to 0, 10% x equals to 100, y equals to 100, 20% x equals to 100, and y equals to 200, right? So we add this row together, that's 0.5, 50% of chance. That becomes your entire universe, right? Nothing beyond this we need to worry about. So basically outside of this, within this smaller fraction of the universe, what is probability, right? Then, in this case, y equals to 0, right? We want to find in what condition y equals to 0. That's the probability. So basically 0.2 out of this, the sum of all these probabilities, which is 0.5, that gives you the result, right? So that's where we have this 0.2 divided by 0.5 equals to 0.4, which of course we observe this table we can find, but we can also use the marginal probability we have before, right? Marginal mass probability function. So px, this should be pxy divided by px, the marginal probability on x, right? We already know that the marginal probability, mass probability function, when x equals 100, the probability equals to 0.5, right? Here's 0.5. And then in here, we know pxy, the joint probability is 0.2. So 0.2 divided by 0.5 equals to 0.4. That's the conditional probability for this, right? That's the result. And similarly, we can calculate all the others, right? For this, we basically, the marginal probability for x equals to 100 is still 0.5, right? So we have 0.5 here. And then the joint probability, so this means x equal to 100, y equal to 100 as well, which is here, right? 0.1. So 0.1 divided by 0.5 give us 0.2. Same thing for this, right? When x equals to 250, the chance is still 50%, 0.5. That's where this 0.5 come from. Same here, 0.5 come from. And then when x equals to 250, y equals to 100, that's this cell, right? 0.15. So 0.15 divided by 0.5 give you this number. Same thing for for y equals to 200, x equals to 250, that's 0.3. Divided by 0.5 and give you 0.6, right? That's how we calculate the conditional probability. So for conditional probability mass function, For discrete random variables, this is relatively straightforward. So you already see this table before, and here I add the conditional probability mass function and the conditional probability density function for your review, right? You can see that now they all look, the two functions are here and they look pretty similar as well, right? So that's the conditional probability for joint distributions. Now we're going to talk about the expected value. So here, let capital X and capital Y be jointly distributed random variables with the probability mass function Pxy, that's certainly for discrete random variable, or probability density function Fxy according to whether the variables are discrete or continuous, right? Then the expected value of a function hxy denoted the expected value of hxy or mu hxy is basically this two, right? This is for discrete random variable. This is for continuous random variable. Very similar to what we calculated before, how we calculated before, right? We always, for one random variable, we always have the probability for each event or each value multiplied by the value of that, and then add them all together. That gives us the expected value, right? And we use the integral to find out the expected value for continuous random variable, but the function is basically the same, right? The function is basically the same. The concept is very much the same. That's how we calculate the expected value. All right, so let's look at one example to understand this better. So it's basically a repackaged example from what we used before. Here, x is a random variable of the value of stock A next month, right? Here's x. Next month, this stock A could worth $100, or it could worth $250, right? And then there's stock B. This is a random variable of the value of stock B next month. Same thing here. Next month it can worth nothing, or be worth 100, or worth 200. The value could be $200, right? So now you want to build your portfolio. Portfolio means, you have a certain number of A and a certain number B and a certain number of different other stocks. That's your portfolio, right? And in this case, what you have is 20 shares of A and 30 shares of B. Now that's what you have for now, right? You don't know what exactly is going to happen next month, but here's the question. What is the expected value of the portfolio next month? And basically, we're trying to, the probability mass function already given right here with actually the marginal probability as well. So now we basically just need to calculate what is the expected value. Again, I'll give you a few minutes. I'm going to pause for 5 seconds. You can pause longer and maybe to take 2 or 3 minutes to calculate what will be the expected value of your portfolio next month. All right, I hope you had a chance to think about it. So the first question, of course, is, what is hxy, right? We said, based on this, right, we said is it need to be the probability multiplied by the value, the hxy, and that will give you the, you need to first multiply them together and then take the sum, and that will give you the expected value, right? So what is hxy here? Now, obviously, here hxy equals to 20x plus 30y, right? This means whatever the x, the value of x, your stock x is, right? You have 20 shares of that. And the same thing, whatever the value of y is, you have 30 shares of that, right? Let's say x is $100 and you have 20 shares of the stock, then that gives you $2,000, right? That's basically how we calculate. So this is hxy. And then the mu, then we basically need to calculate mu, right? We already know pxy. Now we need to calculate mu. Well, if you understand that, it's pretty straightforward, right? So basically we just need to just need to add them, do the multiplication, and then add them all together, right? So for mu h100, that equals to h100 multiplied by p100. That's $2,000, right? That's $2,000. Why that is $2,000? Because 120 multiplied by 100 give you 2,000. 30 multiplied by 0, that's the value of y, give you 0. So altogether, this give you $2,000. And that's the probability of that is 0.2. So you get 400, which basically means that next month there's 20% of chance your portfolio will be worth of $2,000, right? So that's this part. And obviously you can add them all together, and that should give you the total number, right? You can add 100 and 100, 100 and 200, all those together. That will give you the expected value. And I'm not going to do that here, but you can continue on that, right? So that's the expected value. Okay, after talking about the expected value, now we talk about the how to calculate the covariance for two random variables, right? The covariance between two random variable x and y is basically this function, right? The covariance equals to the expected value of this, right? Whatever in the brackets. And this part is basically x minus the expected value of x multiplied by y minus the expected value of y, which we already know how to calculate the expected value, right? Or mean value, basically. And then that the expected value of that. So if we are calculating expected value, then of course we know how to calculate this, right? Whatever inside of expected value, that just for discrete random variable is basically this part. For every value, we multiply by the probability of these values, right? So basically x and y, and then add them all together. That's the covariance of two discrete random variable x and y. And similarly, for the continuous random variable, the covariance equals to two integral, double integral, one on dx and one on dy. And it's the same thing here, right? We have the each value minus their expected value multiplied by the probability density function, and then do the integrals. That give us the result, right? So relatively straightforward. Then let's look at one example, right? The first one is the example already saw before, right? It's the same one. X is random value of value a random variable of the value of stock A next month, and Y is the value of stock B next month. And then we have their joint probability as well as the marginal probability, right? So basically we just need to calculate this. Again, I'll give you 2 minutes to calculate, and then you can pause the video, and then we'll talk how to solve this. All right, so we know how to calculate the expected value of x and y, which are expected here, right? We need to calculate this. I give this two value directly, but I hope you know how to calculate this. It's basically the value multiplied by the probability and add them all together, right? So for x, we know there's 50% of chance the value of the stock is x. So 100 multiplied by 50, that gives us 50, right? Then there's also 50% chance the value of stock A will be 250. So 200 multiplied by 0.5, that's 125. So 50 plus 125 give us 175, right? That's the expected value of x, expected value of x, which basically is the value of stock A next month. Same way to calculate for stock B, right? 0.25 multiplied by 0 give us 0. 0.25 multiplied by 100, that's 25. And 0.5 multiplied by 200, that's 100. So this two add together, well, this three add together, of course, this is 0. That's 0 plus 25 plus 100 give us 125, right? So we find the expected value. So let's give us input for this two value, right? Then we basically just list all the values and the probabilities and calculate the covariance, right? So let's say for this one, this is 1x, next month, the 1x equals to 100, y equals to 0, and that probability is 0.2, right? Then we can calculate its covariance just for this two value. And that's, again, based on this function here. So basically what we do is that we use 100 here, right? Minus the expected value of x, so 100 minus 175. Then y minus the expected value of y. So 0 here, right, from here, minus 125, which is the expected value of y, and then multiplied by 0.2. This is a probability, right? So this part, we put in this part, we multiply by 0.2, give us 1,875, give us this value, right? Same thing here, we can calculate this row. Basically, it's, we still put this number in here, right? This equation going to become 100 because x is still 100 minus 175, and y in this case is 100 as well. So 0 become 100, 100 minus 125 multiplied by 0.1, right? So probably change to 0.1. That gave us 1,875. Sorry, that should give us 187.5, right? Give us this. And then one by one, we can calculate all of them, and the sum equals to 1,875. This is our final number, right? Pretty straightforward, pretty standard. As long as you understand the function, the formula, how we calculate the numbers, it's relatively easy to go follow the steps and find the result. It's straightforward, but a little bit cumbersome, right? Take quite a few steps to calculate. So there's actually a shortcut formula for calculating the covariance, which is this, right? Remember we talked about some shortcut for variance before as well, right? Now here's also a shortcut. We can mathematically prove these are the same. Let's not worry about mathematical proof here, but basically, this is how we calculate it, right? We find the expected value of x multiplied by y. This dot here means multiply, right? Then minus the mu x, this is the value, the expected value of x, multiplied by expected value of y, right? That's give us covariance. This looks much easier than what we have before. Now let's try it and see if this is really give us the result, right? And same here. This is the same question. We are just going to use this function to calculate these, right? And you see that we already have 175 and 125 for mu x and mu y. In this part, we can directly put the number in, right? It's pretty easy to calculate this. So only thing we need to worry is just here, right? The expected value of x and y. And of course, expected value of x, y, that's much easier to calculate, right? So I'm basically putting it here, right? The expected value is for x and y is just x multiplied by y multiplied by the probability, right? So 100 multiplied by 0 multiplied by 0.2 is 0. That's for this row, right? This is what we calculated before. This is what we're calculating now, right? So then 100, so here, basically how we get it is that 100 multiplied by 100 multiplied by 0.1 give us 1,000, right? 100, 200 multiplied by 0.2, 4,000, so on and so forth, right? We can calculate all these values and then add them all together. That gives us the expected value of x and y, right? Of course, this is the expected value. Then we need to minus basically this part, don't forget, right? 175 multiplied by 125. You put this value here, whatever that value is, then you use this value minus that. That should give you the exactly same result as 1,875, right? That's how we calculate the covariance. You see, this way, it's so much easier because we don't need to use this to minus the expected value every time for every row, right? We just need to calculate this, so much simpler, and minus and then minus the result of expected value, right? Multiply together. So, okay, that's covariance. And related to that, it's come to the correlation coefficient. Remember, at the very beginning, we talked about what are the difference between correlation and causality, right? We talk about it. You probably heard it a lot, but this is the first time we are calculating it, right? The correlation coefficient of x and y can be denoted by cor xy or rho xy, or simply rho, which is defined like this, right? So rho xy equals to covariance of xy divided by rho x, which is the sigma x multiplied by sigma y, right? That's standard deviation of x multiplied by standard deviation of y. So that's how we calculate rho. And for any two random variables x and y, the correlation coefficient will be bigger or equal to -1 and smaller or equal to 1, right? In that range. Cannot be smaller than -1 and cannot be bigger than 1. That's the range of it. And what does correlation coefficient really means, right? That basically means x and y share some kind of a trend here. How common or how likely they share a certain trend, right? You see here, in this figure, you can see that x and y basically increase together, right? When x is increasing, so when x is increasing its value, y increasing as well, right? And then you can see that they how to say that they increasing a pretty tightly, right? They increasing together pretty tightly, meaning that it's almost fall onto the same line here, right? You can see a very clear trend here. And in this case, well, they still fall into a very clear trend, right? You can see that one almost on the straight line here as well. However, the effect is negative, right? When x increasing, y keep decreasing, and it's pretty linear. You can see the function is pretty linear, right? And then in this figure, you can see that they don't look like it doesn't feel like there's a clear trend here, right? With x increasing, sometime it's increasing, sometimes it's decreasing. Like from this dot to this dot, x increasing and y is increasing. But then from here to here, x increasing but y decreasing. You cannot see a clear trend here, right? So that's what we want to use correlation coefficient to describe. Basically, based on Wikipedia, a correlation coefficient is just a numerical measure of some type of correlation, meaning a statistical relationship between two variables, right? We want to see if there's a statistical relationship between these two. And for this, one x increasing and y increasing, they almost shows a linear trend. Rho will be very much close to 1, right? In this case, rho will be much close to -1 because when x increasing, y decreasing very strictly. However, in this case, rho almost equals 0. You don't really see a trend there. They don't increasing or decreasing together, right? So that's what rho, why we want to calculate correlation coefficient and what it can describe, right? That's that. So let's calculate that. Let's do a calculation and see if we can do that, right? So we know a lot based on the example before already, right? We already know a lot of information. We know the correlation coefficient is this. We know the covariance is 1,875. We know all this information. Now to calculate the correlation coefficient, basically rho, we already have this. We just need this too, right? The standard deviation. Now, you find the standard deviation, of course, we first need to calculate the variance of x and the variance of y. Then we can do the root and find the standard deviation and then put them there, right? Put them here. So that's what we are trying to do. And to find the variance, we did this so many times, right? It's basically x for each value minus the mean value, expected value, which we also already have, divided by, do the square, and then divide by n, right? That's the variance. So take some time, try calculating that. It's pretty straightforward, and then we can move to the next step. All right, hope you have paused the video and did some calculation. So these are the two values I got, right? It's basically just, to calculate this, that's for x. And basically what I'm going to do is that I use 100 minus 175 do the square plus 250 minus 175 do the square divided by 2, and that give me this number, right? Similarly, I can calculate this number here. This n, of course, becomes 3. And then after doing the calculation, I have this 2 value. And then I do the root and the root value. So basically the root of 5,625 give me 75. And the root of 7291.7 give me 85.4. Then I put this 2 value here. 1,875 divided by this 2 number give us 0.29. So that's our correlation coefficient, right? So what do you think? Do you think X and Y have strong correlation or not? Not so much, right? Not very strong. When it's close to 1 or -1, the correlation are strong, but it's 0.3, more close to 0. They don't have strong correlation, right? Here are some properties of correlation coefficient. For A and C, either both positive or both negative, right? In this case, the correlation doesn't change. The correlation really doesn't change, right? You basically saying X and Y, the correlation coefficient of XY equals to the correlation coefficient of A, X plus B, and B and CY plus D, right? These two are are the same, exactly the same. Now, if X and Y are independent, then rho definitely equals to 0, okay? Say that again, if X and Y are independent, then rho definitely equals to 0, meaning that the development of X has nothing to do with development of Y, right? Of course, they have no relationship at all. They're totally independent. Of course, their correlation should be 0. However, rho equals to 0 does not imply independence. Please make sure, remember that rho equals to 0 does not imply independence. This sentence is true. Independence means rho equals 0. That's true. But rho equals 0 equals independence is not true, right? It's not true. And then the third one is rho equals 0 or rho equals rho equals to 1 or rho equals to -1 if and only if y equals to ax plus b, for a not equal to 0. So it has to be a perfect linear relationship. It can be described by a function, perfect linear ship. Then we can find rho equals to 1 or rho equals to -1. Otherwise, you cannot find that. You cannot get that, right? So that's some properties of correlation coefficient. Again, right, we talk about this. I want to emphasize again, correlation does not equal to causality. Does not equal to causality, right? In this case, I think I showed you this figure before. X is a number of Nobel Prize winners, and Y is number of IKEA stores in different country, right? And you can see the correlation coefficient is pretty high, right? The Pearson R, basically, correlation coefficient is 0.8, almost close to 1. Almost close to 1. So that means for a country have more Nobel winners, it also have larger number of IKEA. But It doesn't really mean a Nobel Prize winners will open an IKEA store. It doesn't mean each Nobel winners is opening an IKEA store. That's why that's the reason. That's the cost. No, we are not inferring any cost, and we cannot infer any cost. Right? There are ways to infer, to try to explore, can help us explore the causality, but correlation coefficient is not one of them. Okay. It maybe hint that we should do the exploration on causality, but not exactly means they're the same. Here are some videos. I'm not going to display them here. You can certainly check them offline. And here is the table shows all the things we discussed about the joint distribution,